In this video, we're going to continue our discussion of Taylor and Maclaurin series. Let f of x is equal to integral from 0 to x sine of 2t squared dt. Find the Maclaurin series for f of x up to and including the x to the power of 7 term. Use this truncated part of the Maclaurin series to estimate the value of the definite integral from 0 to 0.1 sine of 2x squared dx, and also estimate the error of this approximation. It is worth noting that this is not an integral that we can solve by using techniques of integration. So we're going to estimate the value of this definite integral using Maclaurin series. Our strategy will be to start with the Maclaurin series of sine t and use it as a building block for developing the Maclaurin series of the integrand sine of 2t squared. Then we will integrate term by term and get a Maclaurin series for the integral and then evaluate it using the fundamental theorem of calculus. All right, so let's start with the Maclaurin series of sine t. Sine t is equal to t minus t cubed divided by 3 factorial plus t to the power of 5 divided by 5 factorial minus t to the power of 7 divided by 7 factorial. Now let's plug in 2t squared for t. So we get sine of 2t squared is equal to 2t squared minus 2t squared all cubed divided by 3 factorial plus 2t squared to the power of 5 divided by 5 factorial minus 2t squared to the power of 7 divided by 7 factorial, and so on. So wherever you see a t, we plug in 2t squared. So that's very important to get the algebra correct. All right, let's simplify this. We have sine of 2t squared is equal to 2t squared minus, we have 2t squared to the power of 3, so we get 2 to the power of 3, t to the power of 6. The exponents multiply. Divide by 3 factorial, plus 2 to the power of 5, t to the power of 10, divided by 5 factorial, minus 2 to the power of 7, t to the power of 14, divided by 7 factorial, and so on. Now let's integrate term by term. Integral from 0 to x sine of 2t squared dt, and integrate the right hand side. Integral from 0 to x 2t squared minus 2 cubed t to the 6 divided by 3 factorial plus 2 to the power of 5 t to the 10 divided by 5 factorial minus 2 to the power of 7, t to the 14, divided by 7 factorial, and so on. Integrate with respect to t, dt. All right, let's do the integration. So we have integral from 0 to x. So reverse the power rule. We get 2 times t cubed divided by 3 minus 2 cubed t to the power of 7, add 1 to the exponent, divide by the same, divide by 7 times 3 factorial, plus 2 to the power of 5, t to the power of 11, divided by 11 times 5 factorial, reverse the power rule, minus 2 to the power of 7, t to the power of 15, divided by 15 times 7 factorial, and so on. Evaluated from 0 to x. So we have integral from 0 to x sine of 2t squared dt. We found the Maclaurin series of this integral to be 2t cubed divided by 3 minus 2 cubed t to the power of 7 divided by 7 times 3 factorial plus 2 to the power of 5, t to the power of 11, divided by 11 times 5 factorial. Evaluated from 0 to x, we now apply the fundamental theorem of calculus, put the upper limit in minus the lower limit. So we get 2x cubed divided by 3 minus 2 cubed, x to the power of 7 divided by 7 times 3 factorial, plus 2 to the power of 5, x to the power of 11 divided by 11 times 5 factorial. Plug in 0 and it's all 0. So this is the integral from 0 to x sine of 2t squared dt. This is the Maclaurin series representation of this integral. So capital F of x is equal to integral from 0 to x sine of 2t squared dt. Now in the question we were asked to only go up to the term that involves x to the power of 7, so we only need the first two terms. So we get 2x cubed divided by 3 minus 2 cubed x to the power of 7 divided by 7 times 3 factorial. So we use this truncated part of the series up to the x to the 7th term to estimate this integral. F of 0.1 equals integral from 0 to 0.1 sine of 2t squared dt. Let's do that. So we have f of x is equal to integral from 0 to x sine of 2t squared dt. We found the Maclaurin series representation of this integral, and we're only using the first two terms up to the x to the power of 7 term. So we get 2x cubed divided by 3 minus 2 cubed x to the power of 7 divided by 7 times 3 factorial. Now we're asked to estimate the definite integral. F of 0.1 is the integral from 0 to 0.1 sine of 2t squared dt. So plug in x equals 0.1. We get 2 times 0.1 cubed divided by 3 minus 2 cubed times 0.1 to the power of 7 divided by 7 times 3 factorial. So this represents an estimate for the value of this definite integral. So the question is, how good is this estimate? What is the error of this approximation? So if we decimalize this, we get approximately 0.000666648. So the question arises, how good is this approximation? We can estimate the error of this approximation by applying the alternating series estimation theorem, which tells us that if we add the first n terms, the error is less than the absolute value of the first neglected term, absolute value of a sub n plus 1. So let's do that. We have f of x is equal to integral from 0 to x sine of 2t squared dt. We found the Maclaurin series representation of this integral, that's 2x cubed, divided by 3 minus 2 cubed, x to the power of 7, divided by 7 times 3 factorial, plus 2 to the power of 5, x to the power of 11, divided by 11 times 5 factorial, and so on. This is an infinite series. So f of 0.1 represents the value of this definite integral, integral from 0 to 0.1 sine of 2t squared dt, and we're estimating the value of this definite integral with this infinite series. So plug in 0.1 for x, 2 times 0.1 to the power of 3 divided by 3 minus 2 cubed times 0.1 to the power of 7 divided by 7 times 3 factorial plus 2 to the power of 5 times 0.1 to the power of 11 divided by 11 times 5 factorial, and so on. So let's repeat. Basically, we have a definite integral. That's not solvable by the usual means. But we're estimating the value of this definite integral with the sum of this infinite series. Now, we only use the first two terms of this infinite series. So there's going to be some error involved. The question is, what is the estimate for the error of approximating this integral? We know from the estimation theorem, the alternating series estimation theorem, if we add the first two terms, the error is less than the absolute value of the third term, which is the first neglected term. That is absolute value of s minus s2. S is the exact sum of this infinite series. S2 is the sum of the approximate sum of the series when we only add up the first two terms. So the error is less than the absolute value of the third term, which is the first neglected term, this one here. So the error of the approximation is less than or equal to the third term, which is 2 to the power of 5 times 0.1 to the power of 11, divided by 11 times 5 factorial. If we decimalize this is the error of the approximation. And it's a very small error. So you can see that using Maclaurin series to estimate values of integrals is actually very accurate and very productive way of finding the value of a definite integral that cannot be solved by the usual means. All right, thanks.